So this lab we'll be discussing sorting algorithms. Like at the first lab, we saw like two sorting algorithms that were selection sort and insertion sort. So today we're gonna cover other type of learning algorithms that can improve on what we saw previously. And also we will see that there are sorting algorithms that can work in linear time. So can you recall what is selection sort and insertion sort? How does it work? Let's start by selection sort. Do you recall the principle? So if I'm given a sequence, if I'm given a sequence of numbers, yes?
We choose our elements by one, and then searching a place for them. Like we move them until they get to the right place.
Mm-hmm. For which one? For selection sort or insertion sort?
Insertion.
Yeah. So like you should know that the name already describes the algorithm. So when we talk about selection sort, this means that at each iteration, we select the next element. Okay? When we select the next element, it's that we are selecting the next maximum element that we put inside our that our part of already sorted element. Okay? And this maximum element is the minimum element in the unsorted part of the array. What does it mean? This means that at the first iteration, we assume that this part of the array is already sorted, right? And then we have to select the minimum element, okay? So when we look up the array, we see that the minimum element in that part of the array is what? Is 4, right? So what we'll do, we swap 4 and 6, okay? And then we move. And then we move them. So the next step, what did I do? Wait. So when we look up there, the minimum element here is 0, okay? So we're gonna swap it with the leftmost part of the sorted array, or the initial part of the sorted array, okay? So we're gonna swap it with 0. So we swap 0 and 4, okay? And then we move our pointer here. So we start with the pointer here and then we move it here, okay? Because at the beginning, there's no array, it's not sorted. After adding the first element, this part is already sorted. Then we need to select the next minimum element that we're going to add, because we want to find the next element that should be shared. And then next element should be the minimum element in the rest of the array, okay? So we find that it is 2, then we will swap 2 and 6, okay? And we will see that next, this part of the array is already sorted. So what's the next element to put there? Select the element, selection sort, okay? Select the next element. So we say the selection, we return 4. So when we take 4, we put it, what? This is 3, you're right, yeah. So we place here 3, that we swap with 5. This part is already sorted. We do the same, and then we have here 4, and then we have here 5. Then we have here 6 and 7, okay? So this is selection sort. Remember, in selection sort, every time we select the next element, that will grow our part of the array that is already sorted. And this element is basically the maximum element that we will put inside our sequence of already sorted, the part that is already sorted in our array, okay? And this element is kind of the minimum. And for selection sort, we saw that the time complexity is n squared. So the time complexity is n squared. In both cases, in all cases, because we always try to find the minimum element, okay? But when we have insertion sort, instead what it does is that it assumes that, okay, we still have one part that is sorted, but we do not select the element. We just take the next element and we insert to the right position. Does that make sense? So if I have my sequence, let's just exchange three things. So if we have here 3 and here 6, this part is already sorted, right? Right? Now we need to consider like for insertion sort. When we choose 4, we want to insert it to the right position, right? So we start from here, we analyze. Is it the right position? No, it's not. So this means that this element should come before, okay? So we have our element to insert here, which is 4. Is it the right position? Yes. So we replace this by the element to insert, okay? And later on, we have this part of the array that is sorted. And then we select the next element, which is 5. When you select 5, we check, is it the right position? No. So the next element to insert is 5. Is it the right position? No. We copy it there. Is it the right position? Yes. We insert 5 here, okay? And next it will be 3, okay? When we pick up 3, we check, is it the right position here? No, it's not. So the element to insert is 3. Since it is not, we just copy here. 6, is it the right position? No. We copy 5. Is it the right position? No. We copy what is here. 4, is it the right position? Yes. And then we put here 3, okay? And when we pick up 7, we see that, okay, it is already in the right position, okay? So the array sort. This is insertion sort, okay? We just consider the next element at each iteration and we try to insert to the right position, okay? By shifting elements, okay? So what is the time complexity of this algorithm? It's n squared in the worst case. In the best case, what do we have? Yeah, in the best case, we have n. Because when we want to insert, let's say this sequence is already sorted, right? So when I pick 4, I want to insert, I will do almost one iteration, which is one operation, okay? Constant time, because the array is already sorted, okay? So every time you will pick an element, you want to insert in the part that is already sorted, you will do at most one iteration, okay? And then it will just be a linear algorithm. Does that make sense? Well, so this is recall about selection sort and insertion sort. We'll not spend much time there. So let's move on. And then we have the divide and conquer algorithm strategy. We saw that in divide and conquer algorithm strategy, we have a problem. We divide into subsets of problems, okay? We conquer those sub-problems by solving them. Those sub-problems are supposed to be resolvable in the straightforward way, okay? They can be even trivial. And then we combine them, okay? So we can also use divide and conquer to sort a sequence, okay? Or to sort an array. And we see that this approach will give us better time complexity. I mean, better than n squared, okay? So we'll see that later, which is quick sort and merge sort. So bubble sort. Most of you should be familiar with bubble sort. You should know how it works, right? So in bubble sort, basically what it does is that every time that it finds 2 elements that are in the wrong position, it puts them in the right position, okay? The intuition is that by doing so, at each iteration, it will purchase the maximum element to the end of the array, okay? And if you want to write the loop invariant for bubble sort, this is like just to discuss like things that you can see in the final exam. So if you're asked to write like they give the loop invariant for bubble sort, you should understand like what is the at each iteration, Okay, what are the assumptions? So the assumption is that if you have an array like this, okay, at each iteration, this part of the array is already sorted, okay? Then you have to show that it is true before we enter the loops, okay? And then you have to show that it is the maintenance step. It is true at each iteration. So if it is true at the iteration I, it should be true at the iteration I plus 1, okay? And then you show the terminations. Like after the loop, the array will be sorted, okay? So basically, just assume a very naive sequence where you have 1, 2, here you have 4, here you have 3, and here you have 0. What bubble sort will do? Basically, bubble sort will just go through and it will check those two elements. Are they in the right order? Yes. It moves next. These elements, are they in the wrong order? The right order? Yes. It moves next. These elements, are they in the right order? No. It swaps them. Okay? So by swapping them, we will have here 3. I'm sorry. We have here 3 and here 4. Okay? And then it will still check these elements, are they in the right order? No. It will swap them. So it will swap here. Here we have 0, and here we have 4, okay? You see that after this iteration, it has pushed the maximum element to the end, okay? It will do next to the next iteration. It will check, are they in the right order? Yes, it moves. Right order? Yes, it moves. Right order? No, okay? It swaps them, okay? So here you have 0, and there you have 3, okay? And so on and so on. So here, basically, it is pushing the minimum element to the beginning of the array and the maximum element to the end of the array, okay? This bubble sort. What is the time complexity of bubble sort? It will be n squared, okay? Because you have two inner loops, okay? The inner loop will loop through the last index minus 1, okay? So if this is clear, we can move next. So what is most important for us today? So we have quick sort. So quick sort is a divide and conquer algorithm for sorting, okay? As any divide and conquer algorithm, it has 3 steps, okay? We have the divide step. Who can tell us what is done in the divide step? What is done in the divide step of quick sort? Yes? Yes.
We take all elements that are less than picked element on one side, in the one part, and in the other part, we take all elements that are greater than our element, and also have another part which contains elements which are equal to the
Yes. So that's the idea. The idea is that for quick sort, you have one element that we call the pivot, okay? And for this pivot, all you have to do is to push all the elements that are greater than the pivot to the right part of the array, and all the elements that are less than the pivot to the left, okay? So the pivot will be at the right position, okay? And then you have 2 subarrays that is divided. It divided your array into 2 pieces, okay? And you need to perform the same operation to the right, in the right part of the array and in the left part of the array, okay? So what do we do in the conquer step? What is done in the conquer step? So in the conquer state, you apply the algorithm again, okay? And sort the subarrays. And here there's no combined step. And you will see why there's no combined step. Because there's one important notions when we are talking about sorting. Those notions are in place and not in place sorting, okay? What is the difference between them? When do we say that a sorting algorithm is in place? From the lecture, any idea? Any guess? So basically it says that a sorting algorithm is in place if it does not use extra array to perform the sorting. So it performs the sorting inside the same array without creating any subarrays, okay? So even when it creates subproblems, it creates subproblems inside the same array in place, okay? It does not create like other subproblems with in different arrays, okay? Which is what merge sort will do. So if you compare quick sort and merge sort, you will see that merge sort is out of place because it will create different subarrays to perform the sorting. Let's see how merge sort works. You remember how merge sort works? If I am given, let's apply merge sort. So if I'm given, not this one. So if I'm given this sequence of numbers, so let's say I have 10, 3, 2, 0, 1, 9, and 7. If you are given this sequence, you want to apply merge sort. Merge sort just choose the element in the middle, okay, and break into subproblems, like divide and conquer with merge sort. So it will break into subproblems where here you will have a subproblem that will contain 10, 3, and 2, okay? And you have another subproblem there that will contain 0, 1, 9, and 7, okay? These are two independent subarrays, okay? So we will sort these subarrays independently, extra memory. So we need to create this array during the sorting. Because we do so, that's why it is out of place sorting, okay? So later on, what will happen is that you will again split this one into array of size. Here you have 10, and here you have 3 and 2, okay? And here you will do the same. Here you will have 0, 1, and here you will have 9 and 7, okay? We can stop here, or we can go further, okay? But let's stop here. This is a divide step. Till now, the array is not sorted, right? So we can say this one will also be divided into 3, 2, and this one into 0, 1, and this one into 9, 7, okay? So till now, the array is not sorted. The particularity of merge sort is that the sorting is done in the merge step, in the combine step, okay? The sorting is done in the combine step. How? If we consider this part, okay? So if we consider this part, during the merging, what do we have? You have to merge this into biggest array. So we have to merge this, okay? So in the merging step, when you want to merge this one and this one, you just compare which value you should put here. The value that you should put there should be the minimum between the two values, okay? So I compare this and this, the minimum one is 2. So I will copy 2 here, okay? since I have already copied everything that is inside the first array, I just will copy the other array, okay? And here we have, let me write this in different color, 2, and then I will have 2, okay? And next I have to merge them again here, okay? So to merge them here, I do the same operation. I look up these indices at the same time, and I choose the minimum one because I want to find which one is there. The assumption is that this part is already sorted and this part is already sorted. Okay, so I have to merge them in the sort way. Okay, so for that, I compare these two and these two, I choose the minimum. The minimum is 2. I copy 2, and then I move the pointer to the next element here. Okay, and I compare 3 and 10. I copy which one? I copy 3. Okay, and then I recopy what I just copied, what is left in the not empty array or the array that we didn't went through. Okay, and then we just copy here 10. So after the merge step, we have this part, this is sorted. Okay, and then we do the same operation here. Does that make sense? So after the merge step, what we will have? We will have here 2, 3, and 10. We perform the same thing for the other part of the array. So let's copy it and perform the same operation. So in the recursive call, when we call merge, so in the combine step, we have to fill these values. Okay, so to fill these values, we look this one and this one, we pick up the minimum. Okay, the minimum is 0 and 1. Okay, so we look this one and this one, we pick up the minimum. The minimum will be 7, and then we copy the other one, which is 9. Okay, and then we do the same as we did before. We start here and we start there. We look at the two indices, which is the minimum, 0, we copy it here. And then we need to find the element that we put there. So as we copy it from here, we move the pointer to the next index. The other one stays fixed, okay? And then we compare this one and this one, we will take 1, okay? And the last operation is just to recopy. Since we have already looked through all the elements of this part of the array, just copy what is left in the other array, okay? So what is left, it's 7 and 9. Does that make sense? So at the end, what we will have here, we will have 0, 1, 7, and 9. I hope this is visible for you. Is it visible? Yes. So next, we are still combining, okay? So for the last combine step, we have to combine. Have to combine 2, 3, 10, and 0, 1, 7, 9. Okay, so after combining this, what is the size of the array that you expect after the combined step? The sum of the sizes of the two independent arrays. Okay, so we have here 3 and 4, so we have 7. 1, 2, 3, 4, 5, 6, 7. Okay, we use the same strategy as before. We start here and here. We are thinking of what should be written there. Okay, we compare. What is the minimum? Is 0. I write 0 there. Since I copied from here, I will move the pointer there. Okay, and I compare 2 and 1. What is the minimum? Is 1. I copy 1 here and I move the index there. Okay, and I compare 7 and 2. What is the minimum? The minimum is 2. This means here. So I move this here and I will copy 2 there. Okay, and then I compare 3 and 7. What is the minimum? The minimum is 3. I copy 3 here and I move my pointer there. And I compare 10 and 7. What is the minimum? The minimum is 7. I copy 7 and I move my pointer there. Okay? And what is the minimum between 10 and 9? The minimum is 9. I copy 9 here and this array is finished. Okay? I just copied what is left in the other array. Which is left? What is left? It is 10. And finally, I have my sequence sorted. This is the principle of merge sort. Is it clear for everybody? So if you look at the pseudocode or the implementation of merge sort, this is what is done behind. Okay? What is important here is for you to see that this sorting is out of place because it assumes that the merge step takes two independent arrays and merge them into the union that will be sorted. Okay? So in the merge step, we assume that it takes two arrays that are already sorted, it merges them into a sorted array. Okay? And this is out of place because it uses extra memory. Well, now let's look at quicksort itself. How quicksort works and how is it in-place sorting algorithm and how it does not create any extra memory to storage. So let's look at the pseudocode of quicksort. So for quicksort, it takes the input array, it takes the low index and the high index. So it works with indices. We assume that we are working in the same array, but we are giving indices of which part should we look at, which part should we pay attention to, okay? And then what it does, it has one function, partition. It has the function partitions that takes the array, the smallest index and the highest index. It returns a pivot, okay? Remember what is the pivot? The pivot is the element that in the right part of the array, all the elements are greater than that pivot, and in the left part, all the elements are lower than that pivot, okay? After that, it calls the same array, but considering the left part, so from low till pivot -1, this is the left part of the array, okay? And from pivot +1 till high, this is the right part of the array, okay? So it does not consider the pivot anymore because the pivot is always at the right position, okay? And it do the same exactly to the left part of the array and the right part of the array, okay? So the left part will return the new pivot and consider one part and the second part, okay? So let's see how this partition function is done because we said that this is in place. How does it work without creating extra memory? The partition function takes the array, the lower index, and the higher index, okay? And what it does is that it will choose the last element as the pivot, okay? Like the last element in the sequence as a pivot. It has I that starts from the lower index, like the pointer, and it loops from the beginning of the array to the end, and then it compares all the elements with the pivots, okay? If that element is less than the pivot, we perform some swapping, okay? And at the end, we need to return the position of that pivot, okay? So let's take a look at how it works in practice. If we start, maybe we can use the same sequence that we had before. Yes, we can choose this sequence. So if you want to perform the partition on this sequence, so initially we call the partition with the entire array, right? We call quicksort the entire array. So it will choose 7 as the pivot, right? First step, this is the pivot. So we have our pivot here. This is X. From the algorithm, you see that X started at low -1. Low is 0, so X will be somewhere here. I is here. And G is there, okay? At each iteration, it compares from G to low to high. What it does, it compares the value at G and our pivot, okay? So what do we have here? We have 10 and you have 7. 10 is lower than 7, right? What it will do is that it increments I and then you swap I and G. So it increments I, so I will be incremented here, and then it will be swapped with G. So basically what we will do, it will swap 10 and 10, right? So basically we'll do nothing. So next, G will move there, and it compares 3 and 7. Is 3 higher than 7? This means this condition does not hold, right? Does not hold. So we just increment G. So G will go there. And it compared 2 and 7. Is 2 bigger than 7? No. So it keep on incrementing. So G will go there. Okay. And then it finds 0. Is 0 lower than 7? No. Sorry, we did a mistake. So when we are here, we compare 3, that will be 3 and 7, right? So this condition is true. That was a mistake. So since this is true, we swap I, N, and G, okay? So we swap 3 and 10, okay? And G will go here. This is also true, okay? So I will come here, and then we swap 10 and 2, okay? So we swap 10 and 2, so here we have 10, and here we have 2. Basically, this swapping is this operation that we're doing here. And then G will come, we go here. We compare 0 and 7. This condition is true, right? So we swap. We increment I, and then we swap them. So we swap, here we will have. So here we have 0, here we have 10. So we have I here, and G will move there, okay? This condition is still true. So what we do next, we increment I here, and then we swap these two values, okay? So if you understand the idea, is shifting element that is bigger than the pivot to the right of the array, and element that are lower to the pivot to the left of the array, okay? So we will swap 1 and 10. So we have 1 here, and we have 10 there. And then this one will move, G will move there, okay? And then we compare G 9 and 7. This condition does not hold, right? So G will go there, and the loop will end. So G will come here, and we go out of this loop, okay? When we're out of this loop, we swap I plus 1 and I. What is I plus 1? It's 10. It's 10 here, and we swap it with the value that is there. Our pivot was fixed, and the n I plus 1 points to the position of the pivot. So we end up swapping, and then we have here 7, and here we have 10. And then we return what? We return I plus 1. So you return the index of the pivots, okay? So this tells us that this is our pivot index, okay? And the other part of the array is already sorted. It is it's greater than the pivot. So we have 10. So this is the state of the array after we call the first partition. And the first partition, look at the array. Next, we consider what? The left path and the right path. And we still consider the pivot as the last element. So what does it tell us? It tells us that we will next be considering this part of the array and this part, okay? We perform exactly the same operation. So when we take this part of the array, we consider 1 as the next pivot, okay? Everything that is greater than 1 will be moved to the left. Everything that's lower than 1 will move to the right, okay? So let's go ahead. So this is our pivot. We have I here, and G will start there. So what can you see? You see that I'm performing the operation in the same array. I'm not creating any extra array. I'm just performing swapping. Okay. This means this is in place. Okay. So we have G here. We compare 3 and 2, 3 and 1. The condition, this condition does not hold because 3 is not lower than 1. G moves there. 2 and 1, the condition does not hold. G will move here. 0 and 1, the condition holds. Okay, so what we do, we increment I. So we increment I here and we perform swapping. We swap 0 and 3. So after swapping, we have here 0 and here we have 3. Okay, and then we compare this and this does not hold, it moves there. Okay, so last step, what we do, we swap I plus 1 and I. So this means that we swap 2 and 1. So at the end, we swap here and we have here 1, and here we have 2. And it returns the position of the pivot. Remember what is the position of the pivot? Is I plus 1. So it will return this one. This as the position of the pivot. Okay? And next, you will consider this part of the array, and this part, okay? And it was doing the same thing in the other part when you have recursive calls, okay? And then when you will consider the array size 1, so it will not do anything. But for this place of the array size 2, it will swap 3 and 2 because we consider 2 as the pivot, right? So at the end, we will swap here, you have 2 and 3 there. So we will have 3 and 2, okay? And just with this algorithm, you have the array sorted in place without creating any extra memory. Does that make sense for everybody? So most important, what you should remember, the difference between in place and out of place sorting algorithm. Merge sort by default is out of place because it creates extra array, okay? Quick sort is in place. So this pseudocode shows you how we can do it in place. So here we have an example where you have the pivot, which is selected as 3, okay? The next step, everything that is less than the pivot will go to the left. Everything that is less than the pivot will go to the left. Everything that is bigger than the pivot will go to the right. And then you have 2 sub-problems, okay, that you need to solve independently. The next step is that we consider just this part, and we consider just this part as independent problem. But the other part of the arrays, you can see that it's just like gray. This means that we do not pay attention to this part, but this part. But we are doing the operation on the same array, okay? The next step, we choose 0 as the pivot. You see that everything that was greater than 0 went to the left, okay? And 0 itself went to the first position because nothing is less than 0 in our sequence. And the same here. And then we choose 2 as the pivot, no updates because everything that is lower than 2 is already to the left. And at the end, we have our sorted sequence in place. So these steps, they are not extra memories, but they're just showing the state of the array, okay? Well, so now let's discuss the term complexity of quicksort with different assumptions. So if we assume that the pivot is the last element, so this last element also means it's the highest element of the array, okay? Or it's the first element of the array. What will be the time complexity of quicksort? If we select the pivot as the first or the last element, what will be the time complexity? Have you attended the lecture? Have you attended the lecture? Yes, you did. And what was said in the lecture about the time complexity of quicksort? And log n, when? Okay. Let's compute this by drawing the recurrence relation. Okay. So let's assume that the pivot is the middle element. Okay. What is the recurrence relation of the algorithm if the pivot is the middle element? By recurrence relations, recall, I mean something in this form. You have to identify A, B, and f of n, right? So if you look at this algorithm, we are talking about this algorithm. What is A? A is 2. What is B? 2 as well. And what is f of n? Yes, f of n is n. How do you identify that? Basically, you can see that this is the first subproblem, this is the second subproblem. So you have two subproblems. It tells you what is A, okay? Now, what is the size of each subproblem? You can compute the size from these values, right? Okay? So each subproblem is half the size of the input, okay? So B is also equal to 2. Now, what is f of n? F of n is the term complexity of what is done outside the recursive call. Out of the recursive call, we have just this partition, okay? And when you look at the pseudocode of partition, what is the term complexity? What is the term complexity in BICO notation? Exactly, it is exactly n, because it looped through the size of the input sequence, okay? So now we know what is A, what is B, and what is f of n, okay? So we can come back and write down the recursive relation. This tells us that A is 2, B is also 2, and f of n is BICO of n, okay? So we can compute the term complexity using the master theorem, right? So for the master theorem, we have to compare f of n with n power log base b of A, right? So basically A is 2, B is 2. So we have this, okay? Which is exactly equal to n. How is this value compared to f of n? It is equal, so it is equal to f of n. So, which case of the master theorem? The case 2 of the master theorem applies, okay? So this means that T of n round things n log n. Does that make sense? So when we select the pivot as the middle element, the term complexity is n log n. Now, I want you to tell me what happens if the pivot is the highest or the lowest element of the array. What will happen? What will be the size of the subproblems? We are still looking for T of n in this case. What is the size of each subproblem? Yeah, we are not yet about applying the master theorem or more, but you want to derive the recurrence relation in that particular case. What will be the size of the subproblems if we always choose the maximum element as the pivot? It will decrease by 1. Why will it decrease by 1? Remember the pivot. Everything that is bigger than the pivot goes to the right. Everything that is lower than the pivot goes to the left, okay? If the pivot is the maximum element, do you have anything to the right? No, you have just the pivot, okay? And what do you have to the left? All the elements that are minimum than the pivot. So the size decreases just by 1, okay? If next you choose the pivot and it is still the maximum element, okay, nothing will go to the right, but things will remain to the left, okay? So if every time you choose the pivot as the maximum element, the size of the subproblem decreases by 1, and you have only one subproblem to solve, right? So this T of n, the value of A will be equal to 1, and the size of the subproblem will be n minus 1, okay? And the time for merging all subproblem, f of n will be still be n, okay? Is this clear for everybody? Why we derive this recurrence relation? So if it is clear, from here, can you apply the master theorem in this case? So we cannot apply the master theorem because there's some assumptions, okay? It does not even satisfy the expression of the master theorem, okay? There's no B, okay? So, but you remember I showed you in the last lab how you can compute time complexity without master theorem, okay? We can use the tree representation, and we count all the operation at each levels of the tree, okay? So let's apply that. So this means that in the input, we have T of n, okay? It splits the problem into problem of size with the cost n, okay? And what is the size of the subproblem? N minus 1, right? And when you take n minus 1, it will split this, perform the partition in how many times? In n minus 1, right? And result to another subproblem of size, n minus 2. It will take this one, split it in time, n minus 2, and have a subproblem of size, n minus 3, right? It will do so. So it will do so until we have T of 2, subproblem of size 2, right? And here, T of 1, right? And then this will split into 1, and then T of 0. Is this tree clear for everybody? So next, we have to count the cost of each level of the tree, okay? The first level will take n, okay? The second level will take n minus 1. The next level will take n minus 2. This level will take n minus 3, and so on and so forth until it will take 2, 1, and 0. Okay? So what we need to do next, we sum up all the costs at each level. Okay? So we end up having n plus n minus 1 plus n minus 2 plus n minus 3 plus 2 plus 1 plus 0. Okay? This is equal to what? Yeah, so this is exactly equal to sum of I from 0 to n of k. Okay? So this is n plus 1 divided by 2. Okay? And this tells us the time complexity is exactly big of n squared. Okay? So what does this tell us? It tells us that if you choose the pivot as the maximum or the minimum element, quick sort will end up having big O of n squared as time complexity. Okay? So the choice of the pivot is very important. Okay? But interestingly, we have another case where if you choose the pivot as random, okay, the expected time complexity should be n log n as well. Okay? Why? Because if you choose the pivot, you will have a higher probability to have the pivot in the middle than having the pivot as the minimum or the maximum element. Does that make sense? So since having the higher probability of randomly choosing the pivot in the middle, you have the recurrence relationship that will give us two subproblems of size divided by 2, okay, plus n, which is n log n. Does that make sense? So even in the random cases, most likely we will fall into that path. Okay, is it clear for everybody? Well, so let's move next. So next we will discuss counting sort, radix, and bucket sort. So what we saw so far is what we will call comparison-based sorting algorithms, but these particular three algorithms are integer-based sorting algorithms, okay? If we sort with counting sort, which can briefly describe how counting sort works. Any idea?
They keep track of how many each element appears how many times.
Mm-hmm. Yep. Basically, as the name says, counting sort, okay? First assumption is that you know the range of the input, okay? Since you know the range of the input, you can count how many times each numbers occurs in the input sequence, okay? After counting them, you need to output them in the final sorting, okay? So let's take an example. Let me see if you have an example there. So for counting sort, if you assume this example, where we have a list of students, okay? And you want to sort this list by age using counting sort. So there's one important notion in counting sort, which is stability, okay? When a sorting algorithm is said to be stable, any idea? When a sorting algorithm is said to be stable? Yes?
Saves the order of the same elements with the same key. Like certainly data not mixed when keys are.
Exactly. So stability means that it preserves the order of the original sequence. So if you have, for example, if you talk about ages, right? What we know is that students are having like ages, but in this room, like maybe I can be wrong, from 17 to 22, okay? So since we have this range, we can have several students with the same age, okay? So let's just choose a sequence where we have 17, we have 18, we have 17, we have 20, we have 21, we have 18, we have 22. So let's assume that this is our sequence. Okay. And each of these ages are associated to students. Okay, these are like satellite informations. Okay, so here we can have here, let's say for example, Alexander, here Nikita, here Muhammad, here Daria, here Vasily, here we can have I forget. What's your name? Roman. And finally, who is 22 here? Don't want to say. Let's choose one random number, George, for example. So we have each age is associated with with names, okay? So if we assume that, are they sorted in by names? No? No, never mind. So if you assume that we have this order, the sorting is stable if after sorting, elements with the same value preserve the order of the original sequence. This means that after sorting, we have 17 and 17 here, right? We expect the output to have A before M, okay? If A comes before M after sorting, this means that the sorting algorithm is stable. It preserves the orders of the original sequence. Does that make sense? It's just 17, yes, it just seems 17, but implicitly it preserves the order. Does that make sense? So counting sort is the stable sorting algorithm. How? Let's see how it works. So for counting sort, what we will do is that the first step, what is the first step? We know that our range is from 17 to 22, okay? So we need to create an array index from 17 to 22. Let's just add one more one here that we will say it is 20. And this is here. So here we have 17, no, 22, 18, 19, 20, 21, 22. Okay, so in this step, we need to count the occurrence of each of these indices. So we have 17. How many 17 do we have in our input sequence? We count 1, 2, right? We fill here, we have 2 17. How many 18 do we have? We have 2 18. How many 19 do we have? We have no 19, right? How many 20 do we have? We have 2 20. How many 21? We have 1 21. And how many 22? 1 22. Okay? This is the first step. Now, the second step, what do we do in the second step? In the second step, we need to compute the indices. Okay? The first step just tells us the number of occurrences, but we do not know what are the indices, where they should appear in the output sequence, okay? So we have to compute what we call the accumulated sums. So this accumulated sum should tell us, okay, 19 should go to this index of the array, okay? This value should go to that particular index. So in the second step, we compute the accumulated sum, which is like we have the same array, 19, 20, 21, 22. So for the accumulated sum, we have 217, okay? This means that after the index 2, we should already have all the 17, okay? We sum this to what we have there. So this means that from index 3 to index 4, we have our 18s, okay? We also sum with what we have there. So from here and here, we have still 4, and then we sum what is half there plus this one. So we have 4 plus 2, we have 6, okay? So this tells us what is the last index of that particular value. So the last index of 20 is 6. So we should see 21 after 6. That's why we are accumulating the sum, okay? So we have 6 plus 1, we have 7, 7 plus 1, we have 8, okay? So now we know that these are the indices. So now we know that 8 will go to, our 22 will go to the index 8 of our output sequence, okay? So now we need to output the sequence. Step 3, we need to output the sequence. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. So you create the output array of same size. Let me not want to match them. So we have 1, 2, 3, 4, 5, 6, 7, 8. So I have indices from 1. Let me put this where it will be visible, everybody. So we have our indices from 1 to 2, 3, 4, 5, 6, 7, 8. Okay, so what should we do next? What is the next step? Very important step here is what? We have completed the indices. Now we need to output the sorted sequence. Okay, so one idea is to look at the input sequence. So if you have here 17, okay, we read index 17 of the index array, and this value tells us what's the index where we put 17 in the final array. Does that make sense? So I go to my input sequence. For every number that I have there, I read the index and I copy that value to that index. Okay? And I move to the next element. The question is, will this method preserve the order of the input sequence? Will it be stable? If we do so, it won't be stable. Okay? Because it will put the first 17, okay? And then it will put the next 17 before the first 17. That's why we should start from the end of the input sequence to have it stable. Does that make sense? If it's not clear, I can explain again. Right. So this means that to have the stability, we should start from the end. So here we have what? We have 20. At the index 20 here, we have what? Which value? 6. Okay? This tells us that we should copy 20 at the index 6 of the output sequence. Okay? So I copy 20 here, and then I will decrease what I have there. I will decrease to 5. Okay? Because I have 220. I decrease to tell that the next index of the next 20 should be 5. Okay? Next, I pick up the next value, which is what? 22. I read the index 22. It tells me that it is 8. And then I need to copy this to index 8. Okay? So I copy 22 here. And so far, we have covered these elements. And what are the names that are associated to them? We have there W. No, we have W for 20, and we have G for 22. And then we consider our next element, 18. 18 here has index 8. Remember, we have to decrease this to 7. So, and 18 has index 4. So I copy 18 here, and I decrease this to 3. And next I consider and next I consider 21. The index 21 is 7. So I copy 21 here, and I decrease this to 6. Does that make sense? I move next. The next value is 20. When I read in the index array, 20 is index 5. I copy 20 here. And this 20 has the value D. The 18 before was R. And I will decrease this one to 4. I consider the next value, 17. what is the index of 17? The index array tells us that 17 is in the index 2. So I will copy 17 in this index. So I put 17 here, and I decrease this one to 1. The next value that we consider is 18. When I read 18 here, the index is 3. This means I will copy 18 there. So I have 18 here, and I decrease here to 2. And finally, the last value is 17. The index array tells us that 17 should go at the index 1. Okay, so I copy 70 here, and I decrease this one to 0. And I have my sequence sorted. Okay, so if you want to recall what are the indices, so this should be M, this should be A. The other 18 is, and the last 20 is. So you can see that it has preserved the order of the names in the output sequence, the names that are having the same value. Does that make sense? So the sorting is stable. Okay. So in this situation, why is this very important? So let's suppose that you have a list of students that are sorted in alphabetic order. Okay. We want to sort these students by age, okay, and group them into group of same ages, students with the same age, okay? And you want those groups to remain sorted in alphabetic order, okay? So if you use a non-stable algorithm for sorting the student by age, you will first sort everybody by age, okay? This means that it will mess up the alphabetic order sorting. When you will group them, you will still have to sort them in alphabetic order because the first sorting wasn't stable, okay? But if it were stable, what you will have is that even with reaching groups, they will preserve the first sorting in alphabetic order. Does that make sense for everybody? So that's different between. So what you should take away from here, difference between in place and out of place sorting, difference between stables and non-stable sorting. Okay? Very important. Now, let's discuss the time complexity of counting sort. Who can analyze the time complexity of that algorithm? Yes, go ahead. It's just? So you mean if the input is n, the time complexity will be big of n? Not exactly. Yes? Okay, so we have n squared. Why n squared? So you say first step we count. What is the time complexity of counting here? Big of n. And then? And what is the time complexity of these indices? Huh? Big of n? Why n? Because this, the size of this array is not n. Is it n? I have here, look. I have here 1, 2, 3, 4, 5, 6, 7, 8. And here I have 1, 2, 3, 4, 5, 6. So it's not n.
For the second array,
yeah, okay. So, and the last step, I'm talking about this last step, where you complete indices. Which array do you use? You use this array, right, to output this one. But what is the size of this array? It's 6. It's not n, right? And how do we get this 6? It depends on what? Exactly, it depends on the range of the input. Remember, we said that our range is 17 and 22, okay? So if we say that this range is k, okay? What you will see is that this is exactly our range. This is exactly our range, okay? So we are computing indices based on our range. Okay, so if the range is K, what's the time complexity? What's the time complexity of computing the indices? Exactly, so we have here big of K. Is it clear why we have big of K? So K here is the range of the input. And the last step, where we output, what's the time complexity of the last step? Is O of N. So what we do, we just sum up all those operations, okay? So this means that we have big of N plus big of K plus big of N, okay? Using big O notation, we can easily say that this is big of N plus big of K, right? And finally, we can say this is big of N plus K. Does that make sense? These operations are independent. There are 3 separated loops, okay? But one loop depends on K, okay? That's why we have big O of N plus K. Does that make sense for everybody? Well, so let's move next to Radix Sort. So you can see that one important drawbacks of counting sort is that it's only for short ranges. All right. Imagine that you have the range from 0 to 1 million. Okay. Are you going to count the occurrence of each value in this big range? It's huge, right? So that's why we use counting sort for small ranges. But when we have big ranges, we think of Radix Sort. In Radix Sort, the digits are divided, it is sorted digit by digit, okay? From the less to the most significant. And it uses stable sort algorithm, like counting sort. And for each stage, the digit sort should be stable, because if it's not stable, after sorting by the first digit, after sorting by the second digit, you can misorder the sorting that you did before. That's why it should be stable. Let's just pick up an example that we had before. So if we consider So let's consider the same example as we had before. So if we take this example, this means that our input sequence will be 17, 18, 17, 20, 21, 18, 22, and 20. Okay? So for Radix Sort, for the first step, what we do, we sort with respect to the last digit. Okay? So this means that we apply counting sort on this sequence of number. It's like we are applying counting sort on 7, 8, 7, 0, 1, 8, 2, 0, 1. Okay? So we just consider this digit and apply counting sort there. So this will output what? It will output 20 because there's 0 there. The second 20. And next, what do we have? What is the next value? Are you following? 21. We are in digits in Radix Sort, we sort respect to digit per digit. We consider the last digit. We only consider this sequence, which is this sequence, like 7, 8, 9, 0, and so on. So if we sort respect to that part, we have first 0, 0, 1, The next value is, I can see 22, I can see 2 there. And the next value is 17, and then 18. We will not have 19. Okay. We have 2 18. Okay. The second step, what do? We sort now with respect to this digit, to this part of the digit. Okay. So if we sort with respect to this digit, what will be the output? We have 17, and then 18, and then 20, and then, do you understand why it's important to have stable sorting here? So if it's not stable sort, you may have 21, okay, before 22, because it's not stable, and this is wrong, okay? So because the sorting preserves the order of the original sequence, that's why Radix Sort works. Does that make sense? So stability is very important in Radix Sort. Otherwise, it will not work, okay? So let's discuss the time complexity of Radix Sort. We can analyze this. Every time you want to analyze time complexity, think of the operation that you do with respect to the input size. Okay? So here, at each step, what operation do we do? We perform counting sort, right? This means that at each step, what is the time complexity? Exactly. So at each step, the time complexity is n plus k. How many steps do we have? How many steps do we have? The number of digits, okay? If you have 3 digits, we will counting sort 3 times, okay? Remember, if you have, for example, a number that is just 1 digit, you can augment it with zeros, okay? So, yes, if you have d digits, this means that we are applying counting sort d time, okay? So the final time complexity, let me write it properly. D time, the final time complexity will be big O of d times n plus k. Does that make sense for everybody? Well, is there any best case or worst case? Like best case and worst case, will it change the time complexity? Yes, it won't change because in all the cases, we are performing the same operations, okay? So in all cases, expected cases, Radix sort will be d times n plus 1. And then you have bucket sort. So bucket sort assumes that the inputs are drawn from the uniform distribution, and it then split the data into subsets that we call buckets and sort each subset independently, and then it will merge them, okay? And this is applicable for floating points. So if you have floating numbers, we can apply bucket sort for that. So what I want you to do as homework, like extra activity, is for you to understand how bucket sort works and analyze the time complexity. Okay? Okay? Yeah. So, I mean, before analyzing, you take an example, okay? You show the step of bucket sort in that example, and then you analyze the time complexity, okay? So in this table, you have like a recap of most sorting algorithm, at least the most popular one, that are grouped in 2 categories. So you have the comparison-based sorting algorithm that we saw before, which are insertion sort, which runs in the worst case, we saw why it is bq of n squared. And even the expected case is also n squared. Even though the best case is bq of n. But for the best case, in the best case of insertion sort, the array is already sorted, right? So if the array is already sorted, well, why do we need to sort again? So we expect the time complexity to be n squared. That is average or expected running time. For merge sort, we saw that merge sort will always work in n log n. Okay? Regardless the situation, because it will always split into two subproblems of size n by 2, which n is the size of the input. Okay? And it will perform the merge operation in linear time. Okay? So from there, you can draw the recurrence relation and then apply the master theorem to have the final time complexity, which will give you n log n. You have heap sort, which is also n log n. I think heap sort will be the topic of the next lab. Or basically, it will use 3 data structure. You will leverage it to have a sorting algorithm in n log n based on priority queues. That we will see next one. And we have quicksort. We saw that the worst case time complexity of quicksort is n squared, which occurs when the pivot is selected as the maximum or the minimum element. Okay? But if it is not the case, like the pivot, the expected time complexity will be n log n. You will see that in practice, quicksort will work better than merge sort. So that's why quicksort is always referred as the fastest algorithm. Okay. So the expected time complexity of quicksort is n log n, even though the worst case is n squared. But if you randomly pick the pivot, we expect to have n log n. And then you have counting sort that we saw that the time complexity depends on the size of the input and the input range. Okay. And for that, if the input range is k and the size of the output is n, we expect to have counting sort in bq of k plus n, which is typically linear. And then you have Radix sort, which is based on counting sort, which applies counting sort d times, where d is the number of digits that you have in the inputs sequence. And finally, you have bucket sort, which basically will run on worst case n squared, and in the average case, bq of n. So this is the assignment that you have to do. You have to prove that. You have to prove that bucket sort has this times complexity. Okay. So that was what we have to discuss. We have to discuss in this lab, and you have the code first task. So you have this link. Follow the link, and there you expect there to implement counting sort for a particular problem. Okay. So I really advise you to implement this, to have hands-on practice, and also it will help you to better understand what is going on inside. You don't have it on model? It should be on model. What?
There's no elections for, there's no lab slides.
Okay, upload the lab. Sorry.